Okay, hi. I have to admit that the title is somewhat provocative. This was my intention, just to have a lot of questions. The main idea is to begin, just for a while, with a model that starts from microphysics, starts from a specific physical mechanism. Okay. I will present the model, then some observational aspects and its cosmic evolution. Okay, in general, we have three axes that we need to focus. The first one is that the model needs to be based on fundamental principles. It needs to have observational grounding, and also to not be over-complex, which is an ill-defined concept, but we'll go back to this later. Now, a model that is fundamental and simple, but has no observational validity, falls in this category, and is not a good model. A model that is very good observationally and very simple, but has no fundamental basis, usually is a phenomenological one, and falls in this category. Also, we can have models that contain too much arbitrary structures and can fit almost everything. They fall in this place. We would like to have a model that is simple enough. It's based upon fundamental principles and provides good fits. This is what we would like to have. I will not speak about the tensions. There are many speakers that already speak a lot about them. In this talk, I will assume the position that the tensions are physical. At least H0 tension is of physical origin. Okay, my starting point is a paper from Stelios Tsilioukas, Saridakis, and Zerefos. Stelios likes a lot topological stuff and Gauss-Bonnet term. So we have a space-time form where wormholes appear. The Gauss-Bonnet addition to the standard Einstein-Hilbert action provides them with non-trivial topology. So essentially, we have an effective cosmological constant coming from topology, which we call topological dark energy. This is the main idea. Okay, Stelios and the others found the modified Einstein equation, where effective lambda appears. The effective lambda is a function of the Gauss-Bonnet constant, A, and a new term, this one, which has to do with the number of topological anomalies that appear within a specific volume. How these topological anomalies evolve within this volume. But in the original paper, they did not provide a way to calculate this. So we did that. This is our approach. We assume that the variation of the topological characteristic, the Euler characteristic within the volume, comes from the numerical density of each kind of topological anomalies that appear, times the variation of Euler characteristic for this particular category. Okay. So some examples. Black holes have delta chi equals 0. Euclidean wormhole have delta chi equals -2. And Nariae have delta chi equals 2. This is interesting because we can have positive, negative, or 0 lambda effective. And also, this can change over the universe evolution, which is interesting, at least for me. Now, another question is how to calculate the numerical density of wormholes or whatever stuff we implement. We employ this expression where the exponential term contains the difference of the actions between the instanton and the background. Also, in this work, we choose only Euclidean wormholes to have a positive lambda effective. But this is a limiting case. We can have more general stuff if you want. OK, sorry for that. OK, so after all this, putting them in the lambda effective, we have this ugly expression. How we continue? If we differentiate a lambda effective in terms of cosmic time, we obtain equation 5, which is much more manageable. Again, with the assumption of only one instanton kind. Now, using standard reparameterizations, instead of lambda effective having the dark energy density, omega lambda effective, the normalized Hubble rate, and the normalized Hubble constant, we get this model, where G is a known function. This ODE, ordinary differential equation, can be solved numerically using this initial condition and provide everything that we need cosmologically, at least cosmologically. Now, we'll use cosmic chronometers data that probe directly, or let's say semi-directly, the Hubble rate, supernovae type IoT plus calibrators for mu, which means SOES data that probe luminosity distance, and also baryonic acoustic oscillations that probe combinations of the above. This is the expression from luminosity distance for a general curvature. Now, we ask ourselves which are the most probable parameter values given the data. We don't actually care for the parameter values per se. We care for them in order to obtain the cosmic evolution of the model and to assess the model fitting quality. How better or worse is from Lambda CDM and other competing models. OK. So you have to maximize this expression, where chi squared is something very different from the previous chi symbol. Chi square is defined as the sum of individual datasets chi squares. And an individual dataset chi square looks like this, observational value minus theoretical value over error squared. This is not always the case, but this is too technical. OK, we use 3 dataset compilations, namely CC data plus supernovae plus SUS. We add the BAOS in this, and we remove CC. And we sample the likelihood. There's also a lot of technical details that I will not discuss right now because, OK, too boring perhaps for some of you. In order to solve this ODE, you have to do some stuff because it must be solved some million times during the likelihood sample. Some of the results, these are the contour plots for all datasets, all dataset compilations for flat TDE model. The flat TDE model has omega kappa equals 0, obviously. Some comments. The omega matter density is at about 0.25, which is less than omega matter from CMB plus Lambda CDM. And the RD value is much smaller than CMB plus Lambda CDM. This is actually a manifestation of the Hubble constant problem, as we use SOES data that increase H0 value. Indeed, H0 value is about 0.73, the normalized H, to be exact. Here is the non-flat topological dark energy model. Again, the RD is decreased, the H0 is increased, the omega matter is decreased even more, and we have the appearance of cosmic curvature to be about 0.2, however, still compatible with flat universe within 2 sigma. Another comment is about the omega matter value, but we will see it in a few slides. Now, this is the most important, perhaps, in the talk, apart from the model building considerations, how we quantify the relative model adequacy. There are many ways to do that. We have Akaike, Bayesian, deviance information criteria. These are manifestations of Occam razor and information theory and whatever. There's a way to assess which model is better in a certain collection of models that have been fitted in the same dataset. The difference is important between delta IC, which is defined as the IC of this particular model at hand, minus the IC of the best model in the category. Via this quantity, we define degree of belief, which in Bayesian sense the probability of each model to be the correct one, given the data and or model collection. So, for most of the information criteria and for all datasets apart CC Pantheon plus SUS, the non-flat TDE model outperforms Lambda CDM in statistical significant manner. However, the flat TDE model is completely equivalent with Lambda CDM. Okay. We perform a consistency result of both these two models using a criterion at the Big Bang nucleosynthesis. The criterion is essentially the percentage difference between the Hubble rates of the TDE and the Lambda CDM squared, calculated at Z BBN. We observe that all CR values for best fit parameters for all models, the flat models are with stars, the non-flat models are with dots, are well within the 10% limit. So the curvature does not provide any extra effects in BBN era, at least in terms of the background evolution. Okay, about the cosmic evolution, we plot the omega values. This is the so-called fish plot, known to cosmologists. Black is dark energy, red is baryonic and dark matter, and yellow is curvature, blue radiation. So solid line is the model, the TDE model, and the dashed line is Lambda CDM. We observe a shift at about z equals 10, z equals 1 to z equals 100 for the matter in the case of topological dark energy. And here we have the equation of state parameter of dark energy, where we observe that at about z equals 10 behaves as a dark matter, because dark matter cosmologically is defined as a equation of state equals zero fluid. This result is similar for all models, both flat and non-flat, and for all dataset selections, which is interesting also. Now, let's discuss more the transition from dark matter to dark energy, and vice versa, regarding which the area of time in particular. If you assume two components of the dark energy, a pure lambda-like component and a component with W lambda effective, and calculate the effective DM and redo the fish plot, we observe that the fish plot becomes very close to the Lambda CDM1. We have an additional 0.1 omega dark matter today, which means that 12% of dark energy from this model behaves as dark matter today. Okay, let's gather this up. Some key properties. We found a statistical significant preference for not flat TDA from current data, at least some of them. Flat TDE is statistically equivalent to Lambda CDM. We have found a transition between dark energy and dark matter. The model, in principle, allows for changing sign of lambda. It seems to be consistent with Big Bang nucleosynthesis, at least in the context of this criterion. And the model has the same number of free parameters with Lambda CDM. The question is about sigma 8 and H0 tensions. We need to fit CMB data and F sigma 8 data, so we need to have perturbations. These calculations have to be performed before stating anything. And there are two questions. Can we upgrade on the assumptions? And if there are possible imprints of space-time form in other contexts, astrophysical contexts or whatever. For example, blurring of correlations between the blurring of astrophysical images or whatever. Okay, that will be all. Thank you very much.
Okay, thank you for keeping nicely to time. So, any questions? I'll ask a small question. With regards to that last point you have, the imprints of space-time foam, yes. People have searched for small-scale variations in space-time through looking at distant quasars and asking whether or not their images are fuzzier than you'd expect in smooth space-time. What kind of scale of variations do you expect this foam to be at?
This foam is considered to be at Planck scale variation, but they're considered also modification, light scattering, and weak lensing, or different stuff. But in order to sufficiently answer this question, I have to have the calculations performed. Yeah,
but Planck scale is pretty small foam, right?
Yes.
Thank you for a nice talk. So would there also be like non-cosmological tests that you could do, like potentially like within our own galaxy or local group? I mean, would these topological effects show up?
I would like to have an answer to this question also. I would like to have these independent tests, apart from cosmological aspects, to avoid all cosmological related degeneracy. To have direct measurable stuff. There are many, let's say, somewhat old works about that, theoretical ones that calculate amplitudes, scattering amplitudes, but I need to understand specific details on how this calculation performed. I'm mostly observational, phenomenological guy, so this needs a lot of work.
Let's thank Fotios again.